Thanks so much for the introduction, and thanks everyone for joining me for this talk today. I want to give you a high-level overview of what we're going to cover. So obviously from the title of the talk, we're going to talk about tips for parallelizing with Spark. I'm not going to talk about the number of executors you should configure, your driver memory, but I want to kind of go a step beyond and talk about strategies I've picked up through experience that leverage the fact that Spark is such a flexible framework to get a lot more out of your jobs, once you kind of already know the standard bells and whistles that Spark offers to tweak. Next, I'm going to cover a lot of Scala code examples. I personally really like working in Scala with Spark. And so for a lot of these strategies, I'm familiar enough with the other languages that Spark supports, Python, R, and Java, to know that there are parallels to these strategies that likely translate. But unfortunately, today I'm only going to provide the playbook for Scala. And then the third thing, we're going to focus on some specific Scala programming constructs to achieve these different strategies. So we'll do little mini deep dives on those topics. So who am I? I'm a lead data engineer and data scientist from Target. I've been at Target for a few years now. I have a deep love of all things Target and fell in love with them when one opened in my hometown when I was in high school. So when I relocated to the Midwest and found the headquarters was there, and they do work that I love to do, is pretty much love at first sight, so it was exciting. Like my love of Target, I also really, really love Spark. I was lucky enough to work for a startup before Target that jumped on the Spark bandwagon pretty early on. And so it's been a lot of fun working in the space and seeing the productivity it enables. And so I was at the Spark Summit last year. I presented a talk. I presented yesterday also on lessons in linear algebra at scale. So I'm excited to be here and kind of talk through these learnings as well. So here's our agenda for today. I'll give a brief introduction, and then these are the three strategies that we're going to go into in more detail. They're independent. They don't depend on each other. So it's going to be kind of like three mini talks, and we'll go through each one of them in more detail. So as for our introduction, this is kind of what learning Spark looks like for a lot of people. This is what it felt like for me, at least, and for what I see my peers go through in picking up Spark. So you start out, you read the documentation, and you're like, what is this thing? What's a driver, an executor? How do I get the number of executors right, the memory? And then what API should I use, dataset, dataframe, or RDD? And then you get something working, and it's really exciting. Then all of a sudden, your job stops working, and you have to figure out why. So you hop over to the Spark UI to start debugging what's going wrong. And then there it lays out nicely Spark's internal object model. So you learn about what an application is, what a job is. Jobs are made of stages. Stages run tasks. And so you kind of get an understanding of that and what things go into tweaking jobs to make them more performant. And then the next layer of learning is going into partitions, Spark's actions versus transformations and the implications for Spark's planner and optimizer. You learn about shuffling, you learn about caching. And so where I want this talk to fit in is that next layer of learning. So you've kind of gotten your foundation for all the Spark fundamentals, what's really well written in all the documentation. How can we hack this framework to take it even further? And so with that, let's jump into our first topic. We're going to talk about parallel job submission and schedulers. So I'm going to dump a whole bunch of code on the screen. It's going to look really dense, but we'll walk through it. And then these slides will be available after the Spark Summit's over. So for today, for the next 20, 30 minutes, let's pretend we all work at the same content management company. So we work in a system of authors, articles, and comments. And so we want to do some exploration on our data sets. And so you can see in the Scala code there, I created 3 case classes for the entities that we deal with in our system: author, article, and comment, with fields that you would expect to find on each of those. And so I'm going to fill in this explore data method because I want to do some analysis and just play with data. This is probably not the most common way people use Spark. You're either in a notebook or you're in a Spark shell. But what I'm going to do is create a jar, ship it to a cluster, and then kick it off with the Spark submit. And so you can see, you go through the lines. We assume that our entities in our system have Scala companion objects that have methods filled in to know where to grab this data from a persistent store. So we load all of our data sets. I grab my authors, my articles, my comments. And then as we go down the code, we get to line 77 through 96, and we want to ask 3 questions. They're not really complicated questions, but the first one, I want to just join my authors with my articles, grab the first couple elements of that data set, and then just look at it. Just look at my data, see what I'm dealing with. The second question, I want to just look at the first couple of comments in the data set. And then the third question I'm asking, I want to join my articles with their respective comments, and then just look at that data as well. So again, not very complicated things, but we're just playing with the data. So what happens in Spark when we kick this off as a Spark submit? So this is what the Spark UI looks like. So this is our execution starting. I'm not going to go into detail about why Spark created all these other jobs, but I'm going to circle the jobs that pertain to the questions we asked. So the first green box there is our first question we asked. And we see we submitted it. It's been running for around 33 seconds. And then I think back to the questions that I wrote, and they're all kind of independent of each other. It seems like, Spark is supposed to be really good at parallelizing things, so why isn't running them all at once? And that was like really confusing for me at first. I thought I was supposed to magically take care of everything. And so we can see this job completed, and those are our 3 questions there, represented as 3 jobs in Spark. And if you examine the timings closely, look at when they were submitted and how long they ran for, you'll see they're running right after each other serially. Again, it's confusing because they could be running at the same time. So one more sanity check. We look at the event viewer in the Spark UI. We find our jobs, and we indeed see they are running one after each other. So from kicking this off, we learned that Spark took our 3 questions we asked, turned them into 3 jobs, and ran them serially. These jobs don't really seem to depend on one another and seem like they could be run at the same time. So can we make Spark do that? And the answer is yes. So we can leverage Scala concurrency features in addition to the Spark scheduler to achieve this. So we'll take a quick little aside and talk about Scala Futures for 1 second. So Scala Futures, they're a placeholder for a value that might not exist. It supports asynchronous execution. It requires an execution context, either implicitly or explicitly. That's going to define exactly the nuts and bolts of how to run something asynchronously. You can use what's called an await to block and wait for this code running in the background to finish. And I'm showing you a subset on the left in the code example of the syntax supported by Futures, but it's a very rich syntax, and so it's very simple and straightforward to use, and so I'm kind of just showing the parts I use in Spark, but what is there is pretty complicated and supports a lot. So going through this code example here, in a Spark or a Scala main method, I'm setting up my executor service to just be a fixed thread pool of 10 threads. I'm going to wrap that in an execution context with which futures need to be able to run. And then you see I've set up 3 futures there, future A, future B, and future C. And so the syntax is very straightforward. You just wrap the code that you want to have run asynchronously in a block. And then you can either implicitly or explicitly pass in that execution context. And the really neat part, I think, is the syntax for future C. So you can actually support managing dependencies and creating a tree of these dependencies of your futures through 4 comprehensions in Scala. So that future C there, it's depending on future A and future B to complete. And so once those asynchronous operations are complete, then it can execute the code block in the yield in the background. And then you see going further down, we await for our future A to complete. We call await.ready. And then alternatively, we can call await.result and actually grab a value back that our future produces. And then as a final step, we have to shut down our service of the thread pool and then close out our resources. So how do we take those Scala futures and then kind of move them into the Spark world so that we could ask our questions concurrently? And so the first thing we need to do is pull in a reference to an implicit execution context. And so you can see in the signature for this explore data method, we already have an implicit argument list which takes in a Spark session. And so I just added an execution context there. That's going to define outside of this code, how many threads are available in a thread pool. And then the next thing we do is we take each of our questions that we were asking and we wrap them in a future block. And so really, you hardly had to change anything other than wrapping your existing code in future. And then at the bottom there, we wait. We wait on all of these futures to complete. So then that signals that our job is complete. And then not shown here, we need to shut down that executor service and make sure our thread pool is closed out. So what happens when we send this to a cluster and kick it off? So I circled again the jobs that pertain to the questions we're asking. You see the 3 questions there. And if you squint and look closely at when they were submitted and the duration of these jobs, it seems like they're starting to overlap with one another, which is exactly what we were hoping for. And then doing a further sanity check against the event viewer, you see that our jobs are indeed overlapping and running concurrently. So this is how we can get more throughput, more concurrency through our Spark jobs. So one quick note, you can go through all this effort and rework all of your code into futures, but then not see any benefit. You could have done the same thing that I just did, but then your jobs still run one after the other. And why that might happen is because the default scheduler in Spark is FIFO. So if you have a job that's going to consume all the resources available in your cluster, then even though Spark might know about other jobs it could run, it's still going to be consumed by that one job. And so one way you can get around this and kind of pump other jobs through at the same time is to switch over to the fair scheduler. And so I've created a code snippet here to demonstrate how you can turn that on. So you do this through the Spark session. So you'll set Spark.scheduler mode to fair. You'll set Spark scheduler allocation file and point it to a configuration file where an example of that is also shown. You need to specify the various pools that you want to use for scheduling. So I've set pool A here. You set the scheduling mode to fair or FIFO. You set the weight of that pool so that kind of denotes priority. You set the minimum share, which is the minimum number of resources that pool needs to be able to grab to start running jobs. And then finally, for any thread that's going to be submitting work in Spark, you need to set a local property. You need to set the Spark scheduler pool and say what pool you want that thread to be submitting its jobs to. So this is useful, in a couple of contexts, but if you want to see progress on more jobs at once, you have a huge job that's going to take the whole farm you have running, but you want to see progress on some of these smaller jobs that can help you kind of get resources allocated in a more fair, round-robin type manner. And so when you actually turn this on and you want to check it's working properly, you can check the Stages tab in the Spark UI and then just sanity check that you have 2 fair scheduler pools running, or at least it depends on your allocation file. You'll always get that default FIFO one, but you should see now that I configured pool A, it's indeed there. And then you can check your running stages and then see what pool they ran in just to sanity check that the fair scheduler works as you expect. And I didn't include a screenshot here, but if you go to the Jobs tab, it'll say Scheduling Mode, and you should see fair there as well. So I do this all the time now. It doesn't really matter, what I'm building. When I'm doing some sort of ETL job, I will just turn the whole thing into a DAG of futures. I'm not going to scrutinize my code and say, is Spark going to turn this little part into a job or that little part? I will just do it myself where I find the independent blocks of code and kind of, create the tree, create the DAG, and then leverage the benefit you get from, maybe being able to push more through concurrently if the resources allow for it. So the takeaways. Actions in Spark, collect, take, write to table. This triggers Spark to do things, triggers Spark to create jobs. Spark can definitely handle running more jobs at once. You just have to tell it to. And you can accomplish this in Scala, and I'm sure other languages, but in Scala specifically by using futures. And then you can also further configure the way the tasks get run in the order by changing out the scheduler. So why do you want to do this? And we work in a shared environment, a target. So, we're going out to this cluster, we're grabbing resources for our job. And so it's kind of a shame if you kick off a job, but then a lot of your resources are going unused. And so this can kind of maximize the resource utilization for what you're taking. And then as a great byproduct to you as a developer or data scientist, you're maximizing the concurrency and hopefully speeding up your job, speeding up the efficiency. And so then you can also, take it a step further and use the fair scheduler if you want some of those smaller jobs that might be pushed aside to the very end if you want to see progress on them sooner. And I think fair scheduling is probably most notably used in shared environments when you have multiple users kicking off jobs and you want to more fairly allocate resources so more people can see their work being executed. So that was parallel job submission and schedulers. Let's jump right into partitioning strategies. So this is what a first experience with partitioning looks like for a lot of people. So, I want to just check out my authors table and just grab some raw data between a start and an end date range. And say this is a Hive table. So I'll call Spark session.sql, pass my query in, and then get this back as a data set of authors. And so this is what my data might look like on disk. And so these are what my partitions are going to look like in Spark. And so you can see they're kind of messy and ragged and all over the place. And when you work in Spark for a little bit, you realize that having even partitions is really important to having your jobs run reliably and performantly. Most notably, people understand the pain of having uneven partitions when you see your job run really quickly and then it gets to the last 2 tasks and it just sits there for 10 minutes. Usually it's indicating some sort of problem with data skew. And so the next thing you would do to kind of fix the situation is execute a repartition. So you can see I've copied that same code block on the left, put it over on the right, and then just called repartition 5. So that's going to even out the buckets of data into 5 even partitions. And so going into partitioning a little bit more, you have 2 options. You can do a repartition or a coalesce. Both have their pros and cons. So repartitioning allows you to go up or down in the number of partitions, but what it does is it does a full data shuffle. So it's going to maximally be moving data around. But it has a rough guarantee of evenness over large data sets. Whereas coalesce, you can only go down in the number of partitions, and it tries to reuse existing partitions, and it tries to minimize data movement. But the problem there is if you're starting out with really skewed data to begin with, you might, in the long run, end up with more uneven partitions using this method. So it's kind of a trade-off. I end up using repartitioning a lot, but you just kind of have to see for your data set what's more performant. And so you can do partitioning on all of the APIs, dataset, dataframe, RDD. But it should be noted that custom partitioning is really only supported at this point on the RDD API, which is more or less considered legacy at this point compared to datasets. And this is specifically provided on the RDD API through implicitly added pair RDD functions. So in our example here, we grabbed an article data set out of Hive. We turned it into an RDD, and then we index our articles by their ID. So having a tuple of that shape automatically applies the pair RDD functions implicitly. And so then you can leverage the RDD API partition by, and you can pass in a custom partitioner. And so Spark by default ships with 2 partitioners, the hash partitioner and the range partitioner. I typically use the hash one most of the time, and basically that's computing some hash function on the keys to figure out how to bucket the data. Whereas the range partitioner is taking, I think, 1 pass of the data to determine ranges, and then applying that function to, again, determine based on keys how to bucket data. So these are the 2 that are supported out of the box, but you have the flexibility to create your own if you want. So you can create a custom partitioner by extending Spark's partitioner class, and I'll give an example of that in a bit. So why would you want to do kind of non-standard partitioning? How could that be useful? I mean, you can just call repartition, but why would you want to do anything more than that? And so the first example I can come up with is co-locating data for joins. So in this code example here, I pull an article data set and an author data set, and I want to join these 2 data sets together. So you can imagine that the articles data set has author IDs that are kind of randomly distributed throughout the partitions. And then you want to join that over to authors based on the author ID. And so this could be considered a wide transformation in Spark, where all these partitions kind of have to talk to each other, and it's a lot of cross chatter and can lead to a really heavy shuffle stage when trying to carry out this join. And so we can hopefully cut down on that by taking a step to organize our data beforehand so we can cut down on the cross chatter. So you can see here I take the next step on line 26 and call partition by, and then provide the hash partitioner to try and allocate all the articles by a given author within partitions, and then join that to authors. And so I'm trying to provide an example visually of what that might look like. So again, the author's data set's on the left, or I'm sorry, articles are on the left, authors are on the right. You can see it's kind of randomly distributed which authors wrote which articles. But if you take a step to organize that data on the right, then it can make your joins a little bit more performant. So that's one example of how to use more custom partitioning. So another example I have of using non-standard partitioning is to if you want to get to a point where you can operate on partitions wholesale. And so I put together a code example here to try and demonstrate why that might be useful. So here I grab a data set of articles, and I want to grab all of the articles for a given author. And for each author, I want to compute some metrics on all of the articles they've written. And so say I want to take their articles and compute the top vocabulary words that you see. I want to get the average length. I want to get the similarity scores between all of their articles. You can imagine where you could string together, map and reduce calls and index articles by an author, create a list, keep concatenating that list as a reduce. But you can imagine where that might start to look messy in code, especially if you're trying to do a bunch of these metrics at once. And so what you can do is take this data set, index it by the author, and then partition it by what I call a unique ID partitioner. This is something that I wrote, and I'll show you on the next slide what it looks like. But basically, it's going to take all the unique IDs you would expect to see in that key, and then just guarantee that all of those IDs within a partition are the same. So this is getting the data grouped into partitions that are articles just for one author. And so then you can leverage Spark's map partitions API, which just requires that you provided a function that takes an iterator of one object, provides an iterator of another object back. And so it proceeds that you can grab the list of all of the articles out of this partition, lines 42 through 44, execute all of your metrics wholesale, and then get that into a good format, and then just keep trucking with your Spark transformations. And so here's what the Partitioner Cost looks like. I've been working in Spark for a few years at this point, and this is really the only custom partitioner I've ever had to write. But I'm sure other people could come up with great use cases for other ones. But it's not a lot of code, and it's pretty straightforward. You just have to implement two abstract methods, get partition and num partitions. So takeaways. Partitioning can help you even out your data skew, so you can get more performance out of your Spark job. All of the APIs support, repartition and partitioning operations. The RDD API in particular is the only one that's going to support custom partitioning. And then you can use custom partitioning if you want to have more fine-grained control over what exactly gets grouped together. And there's definitely expense involved with repartitioning. And so you have to balance that against the expense of the repartitioning versus doing operations on less organized data. Okay, and so the final topic I want to dive into is distributing more than just data. So this is what Spark code typically looks like for me. I'm sure it's different for everyone depending on what language you work in and what API you prefer. But say I want to just explore some data and I grab my author's data set. I'll be doing some mapping, some joining, maybe getting into a format where I'm going to start doing a count, by reducing over a key. And so these, functions that you pass all the Spark APIs are kind of small and simple and straightforward. And I was kind of wondering, the API is so flexible. It's just taking functions, and you got to adhere to a contract there. But could you really just put anything you want in those functions? And it turns out the answer I found so far is yes. And the first example I have pertains to distributing scripts. And so this is kind of something I stumbled upon when working as a data engineer supporting a data scientist for a specific project. So you often learn, with different facets of math, there are de facto languages people love using, de facto libraries, and it's really different for the different focuses people have. And so I was trying to figure out a way to kind of enable our data scientists to still be productive and use the tools she liked to use, while also, accomplishing what I had to do and help scale up this system. I couldn't just go to her and say, hey, can you just learn Scala, no big deal, and can you pick up some Spark too, so you make my life a little easier. And then on the flip side, I didn't want to have to constantly take what she had written in another language and then constantly keep converting it over to Spark and Scala so I could, keep this scaled up. And so what I learned is that you can leverage the Spark APIs to actually execute scripts in parallel. So if your data scientist is working on some problem that is parallelizable, it's a linearly separable problem, then that's a great candidate to actually distribute the execution of what they're doing through a script. And so we can go through the example here together. So we have this explore data call, and I got this script from my data science peer called super awesome PyRubySkill executable script from peer. First step is you're going to take, you need to tell Spark about the file. So you're going to call Spark session.sparkcontext.add file. And so what that does is it ships the file out to all of your executors that you have configured. The next step is to broadcast the name of the script, and we'll leverage that later on, within the task. And then if we go down here, we see what we're doing exactly is grabbing a data set of articles, and then for each one of those articles, my data scientist script is going to create a sentiment analysis report on the text contained inside of that article. And so I'm going to build a command, just like you'd see on the command line. And so I call Spark files.get, and then the broadcast of the script name. That's on line 78. And so what that's going to give you is the fully qualified path to where that script exists in the container for that executor. And then you just pass in the arguments as you would normally on a Unix command line. And so say the script requires you pass in -t and then a whole bunch of text for the article. And so where the magic happens, and it doesn't even really stand out, but on line 84. So what I'm doing is leveraging Scala sys.process package. And they provide a DSL for executing processes, and so I just call exclamation point, and that's kicking off an external process through Scala, and it blocks on that process being complete. And so you can communicate with this process through all the normal ways. You can communicate through standard in, and then standard error and standard output. You can communicate through the file system. And so her particular script, it communicated to me through standard out. It passed me some JSON back. So I picked my favorite JSON parsing library, read the sentiment analysis report from what was returned, and then got it into a good format, and then just kept chugging with my Spark transformations. So this was earth-shattering for me that you could do this. It's really opened up the doors for more things that I thought Spark wouldn't be able to accomplish. So I can kind of pull in more computation that wouldn't normally work well with Spark, due to serialization or other reasons, and kind of keep it independent and let my data scientists work in the world that they like to work. So just a quick view of Scala sys process. I pulled this from their official documentation. So it's a very rich DSL for running external processes directly from your Scala code. You can do really fancy things. Look at the top line there. It looks like a Unix shell command with a whole bunch of piping. And there's so much there, but really, literally, the only thing I use is that exclamation point to kick off my external process. So I want to put some gotchas here. You'll read this list and you'll think, well, duh. But I figured I should call them out because these are definitely things I ran into. So first, you want to make sure that you have the appropriate amount of resources provisioned when you acquire your Spark cluster. You want to understand the memory profile, the CPU profile of these external processes that you're going to kick off. You want to make sure that your external process is built for the appropriate architecture that your cluster runs on, and then all the dependencies are there that you need, including licenses or other packages or whatnot. If you run more than one executor core at a time, you're going to have multiple of these processes running next to each other, and so you just need to make sure that they're built in a way that they're not going to step on each other's toes. Which kind of brings me to the last thing. If you're going to do any sort of communication through your file system, you just got to make sure, keep an eye out for file system collisions. Don't have the script rewriting to absolute paths or the same temp directory. So I tend to create, these temp directories, execute in there, and then, clear that out as a result. Okay, and so the second thing that sort of blew my mind in the flexible ways you could use Spark APIs was distributing data gathering. So APIs are here to stay. That is a really common way people get data these days. And when I support peers at Target, a lot of people ask, I have data in Hive, that's fine, I know how to grab that. But I have a whole bunch of data I have to get from APIs. Can I use Spark to do that? It doesn't seem like you should be able to, but you absolutely can because of how flexible these APIs are. So if we look at the code example here, I pull a data set of articles, and say my company is working with a third-party analytics company, and they are hosting, analytics through an API that we need to grab so we can understand information about how people are receiving the articles our company is writing. And so you can see I grab my data set of articles, and then I call map on each one. So this is distributed out through Spark. I use my favorite HTTP library to generate an HTTP request. And I kick that off for my article in question. I grab the response back. It's usually JSON. And then use a JSON parsing library to make sense of the response. And then again, get it in a good format for the analysis I want to do in Spark. And then keep checking with my Spark transformations, maybe write it out to a table. And so, this was just super exciting that you could leverage Spark to, not only kick off scripts, but then also hit APIs to kind of handle some of your data gathering. So some gotchas here. You want to make sure you carefully manage the number of concurrent connections you have to your APIs. You might have some SLA, limits with the service provider you have, or it might cost a bunch of money, or it might be some internal team, and you don't want to anger your buddies by taking down their APIs. So you can leverage, partitioning, or, be smart, in your map or map partitions call about how many concurrent API connections you're allowing your job to make at once. And then another thing I'll caution, it's not like hitting Hive or hitting a relational database. These are kind of inherently more glitchy interfaces to interact with. So you want to make sure you use proper error handling and then do a lot of retries, or configure some sort of back-off retry in case there's momentary outages. So takeaways here, the flexibility of the APIs in Spark really allow you to kind of hack the anonymous functions you can pass in more ways than what seems most obvious. And the two examples I provided are distributing scripts to be run as external processes, and then also distributing API calls for data gathering. So that's it. These are my tricks that I tend to use these a lot at this point. It's just kind of exciting to see, the productivity they enable and the speed ups I've gotten out of, certain Spark jobs by doing these things. So it's exciting for me to be able to share them with you all as well. And so here's my quick shout out for Target. So we're hiring like everybody else. Consider working for Target. We're hiring in the data science, data engineering space. Retail is a really fun world with a lot of data and different domains. And we have offices all over. We're headquartered in Minneapolis. Check out our jobs board if you're interested. Feel free to contact me. I can put you in touch with the recruiters. And then I just want to thank the Spark Summit for having me. Thank you to Target for setting me. Thank you to the wonderful people I work with at Target. And then thank you to all of you, vibrant Spark and Scala communities. I definitely learn a lot from everyone here through the questions, blog posts, conference presentations. So with that, I guess I do have time for questions. I ran a little faster, so thank you.
So originally I said there wasn't time for questions, but as Anna just said, there actually is like 5 or 6 minutes. If you have any questions, please line up at the microphone on that side or on this side, and we'll alternate taking questions from those. Thanks.
I have a question. So you are using futures to perform an action, like in your example, I think you're using a collect and for each.
Yeah.
Given that Spark or Scala is typically lazy loaded, if I was to place say a command to go get data from an external data source, is there any sort of tricks to make sure that when that eventually happens, it will still happen inside the future?
Yeah, so I have that concern too, because when you do create the DAG of features out of all of your code, you're not only doing it on what's considered an action, but also the upstream transformations that are lazily evaluated. And I thought that would be a problem initially too. It hasn't been a problem in practice. I've tested it out, and I don't know the nitty-gritty of what's actually going on inside of the optimizer planner. But what I sometimes see is kind of duplicated maybe stages being created, but then they're skipped immediately. So it's smart enough to know that I've already done this to skip it. And so I was worried about the same thing, and I've tested it out, and it works like a charm. Yeah.
Yep. Thank you.
Mm-hmm.
Hi, We have a quick question. So the way how we coding is exactly the similar things you code. We're using the Scala.api a lot, combined with Scala, Spark. So
You're talking about hitting external APIs?
yeah.
Yeah, okay.
So the question is, based on this time Spark submit, we know there is a new product from Databricks called Delta. So do you have any ideas how to implement the same style, coding style on Delta for App13? Because when we looking at this topic, the first question to keep in mind is how we implement this.
Yeah, I'm less familiar with Delta at this point. I haven't dug through the APIs to see how this translates, so I probably don't have a great answer there.
Okay,
Sorry.
so it's okay. I know we have another question.
Oh, sure.
So for customer partitioner, we also implement the same strategy. So, but in our case, we noticed that for dealing with large data set, by using RDD customer partitioner, we have some memory issues. Do you guys deal with the similar issues, and how you solve these issues?
I mean, I guess it probably depends on what you're partitioning and how you're partitioning by. Like, I wouldn't just use that unique ID partitioner on anything without understanding like the relative sizes of what it's actually going to create. So I feel like I'll use that if it makes sense, like for the data set in question, and then make sure the partitions it's going to generate will actually fit into like a reasonably sized cluster. And so I think it's really case by case. Like there are some cases where I realize I can't use that unique ID partitioner, so I'll try to figure out another way to do it with the hash partitioner.
I see.
And then do a map instead.
I see. So you guys have multiple solutions deal with different size of the source, right?
Yeah, I think it's just case by case. Like if this works, great. If not, you kind of have to like, think of another solution, yeah.
Got it, thanks.
Yep.
Hi, I saw an example where you were making an API call, but you were also repartitioning the data based on the number of API calls you want to make.
Yeah.
Was there a logic behind that, or why is
Yeah.
repartitioning required before you make the API call?
Yeah, so I wanted to call out, like, in case you're dealing with some API that has an SLA for how many concurrent connections you can make to it. If you repartition your data into that number of partitions and then execute, your map where then you're going to hit the API, you're going to be limiting the number of concurrent connections based on those number of partitions. And so that's one way. You can do that as long as when you repartition to that number, it doesn't create ridiculously huge partitions. So if that happens, you have to come up with some other way to manage it, but that will kind of limit you if it's a reasonably sized data set.
And what if there's no, or the API limits are fairly huge, fairly large? You don't need to repartition, or you would still recommend repartitioning?
Yeah, I guess if they're really huge, then, you just kind of have to compare it to your data set and see if that all matches up.
All right, thank you.
Yeah.
So I want to know, using the futures, like how many concurrent threads were able to kind of, at some point I'm sure you're hitting the driver memory limitation. So what is the recommendation, or what was your experience in production, how many concurrent threads you were kicking off?
Yeah, that's a good question. I don't think I did an exhaustive experiment there. I typically kept it between 10 and 20. I feel like I've come across other people doing way higher things. But for my purposes, the jobs I was writing maybe had 20 maxing distinct elements I was trying to do. So it didn't make sense to do anything super crazy.
But does Spark natively support any queuing in front of the scheduler, or is it mostly, it just does concurrent? Like if I say phase scheduling, and let's say I queue 10,000 threads, does it actually queue it up, or does it actually try to do a phase scheduling of all of them and then screw up the driver?
I haven't found the latter case. I think it just goes directly into the scheduler's queue, from what I can tell.
Okay, cool.
Yeah.
Thank you.
So I had a question regarding the Python external analytics run from your Scala code.
Okay.
So we use Yarn Resource Manager. So do we have to do anything special in order to package or send it to the executors?
Yeah, so I did this once for one data science peer who was doing things. She had Python wrapping another library. And I think we did have to ship out a custom Python, which was huge. So that's not ideal. So yeah, we did have to set up a mini Python environment there, and that thing also depended on a license. So it looks really simple from the example where you're shipping out one file, but you might need to be shipping out a bunch of files, and there's potential they could be big. So you might want to like look into whether you can have some network attached drive to all your executors, so you don't have to actually like move that. But Python was a little trickier than some of the other languages that were more self-contained.
Okay. One of the follow-up question on the fair scheduler. So what we have noticed is if we have a lot of long-running jobs, and in between we have a kind of a multi-tenant cluster, and a few quick queries we want to send through to the Spark cluster. We've seen FIFO perform better with the fair scheduler with multiple pools.
Okay.
We've seen FIFO works better than fair. Do you have any insights as to why that will happen?
You're finding that FIFO is working better for you?
Yeah, even with multiple pools. So we have
okay.
multiple pools, and we see on the Spark UI that multiple pools are being used, but FIFO seems to be letting jobs, the smaller ones go through rather than fair.
Oh, so you're saying it's letting them go through sooner than the fair would?
Exactly. Yeah.
Yeah. I guess it depends on like it's kind of hard to predict what the planar optimizer is going to say to do. Like if you're lucky enough that your small jobs come at the front, then it makes sense that with FIFO they're going to get pushed through quickly, because if you use the fair, it's going to allocate resources to that big job, which is then going to slow down these small jobs because it has to go alongside that big one. So that sort of makes sense, I think.
Okay.
And so maybe you could rework code with futures to submit those small jobs first, block on them, and then submit that big one, if you can kind of isolate where in the code they're getting kicked off.
Thank you.
Mm-hmm.
All right, that's all the time we have for questions. If we could give Anna a big round of applause. Thank you.